Hello, my name is Avik Chaudhary, and I'm part of the PyTorch compiler team. I joined the team earlier this year. Last year, we announced PyTorch 2 compiler stack with Dynamo and Inductor and all of that. If you're not familiar with that, I'll probably give you a brief introduction through the talk as and when required. But since then, a major focus of our team has been this new export path, which I'm going to talk about today. All right. So this builds on the technological kind of breakthroughs of torch.compile, except that here we are no longer talking about compiling just in time as your program runs, but rather completely ahead of time. All right, so I gave a version of this talk yesterday at the PyTorch conference, and I had 10 minutes to give that talk. Today I have more time. So I will linger on a few topics for a bit longer, but broadly this talk is structured in three parts: why we need export, how we built export, and finally what export looks like. So let's start with the why. Like, why does PyTorch need a sound whole graph capture mechanism? All right, so the short answer is that it's often necessary to do so. Remember that with torch.compile, there is a lot of back and forth with the Python runtime. So for example, if you call a function, Dynamo grabs the bytecode of that function, and then we compile it to a subgraph. But if we run into something, as we often do, if we run into something that we cannot compile, we would fall back to the Python runtime and let it rip for a bit, and then come back, resume compilation, and then get another subgraph, right? So if you think about how torch.compile works in a timeline, you can think of it as a series of like compiling and then falling back to Python, compiling, falling back to Python, and so on, right? And graphically, you can think of this as like subgraphs which are connected by Python glue, right? So, but now imagine that you have environments that must be completely Python free. For example, devices that have various hardware constraints, right? Or servers that don't want anything to do with Python. Like, God knows why, but they don't want anything to do with Python. I'm just kidding. There are good reasons why. So for those environments, you do not have this fallback to Python. So you need ahead of time kind of full graph capture, right? Besides, if you do have a representation of the entire computation that your model was going to perform, it's often desirable to have this kind of representation because you can do all sorts of special purpose optimizations on top of this, or you can bake in special assumptions that a general purpose compiler would never consider to do, right? So the possibilities are endless, so to speak, in this case. So that's what we are going after, right? So let's say you're sold on the idea of whole graph capture, right? Now, why does it need to be sound? Well, hold on now. We are talking about capturing a model once and for all based on some measly example inputs. Like if you're familiar with how things are compiled in PyTorch, like you provide some inputs and we try to kind of trace through the graph and through the code, and we get some kind of code generation from that, right? So, however, in this case, you will capture a model once and for all and then run it on potentially many different inputs in the future. So what's to say that your code won't crash when you do that? And what if it does? Like, imagine debugging a runtime failure far away in space and time from when and where your code was compiled, right? You have no idea what happened in the interim. So it's a nightmare to debug these kinds of failures. And then if you finally do manage to find the root cause and fix your code, you have to go through the whole process again and deploy your code. And then what? Like, pray that this never hits you again, which is a bad idea. All right. So what do I mean by soundness anyway? It's very simple, right? Put simply, it's just that if you feed in so-called valid inputs through your code, you will get correct outputs, right? So it's easy to understand what this means. Of course, the catch is that you have to understand what valid and correct, right? So we infer what valid inputs are based on your example inputs. So we generalize them slightly. If that's not enough, if you want more generality, tell us exactly what you mean by valid inputs. That's basically our stance. As for correct outputs, it basically means whatever the original code would have produced given those inputs, right? So we are, let's say this orange kind of input is the input that you used for exporting. We're trying to kind of generalize the cloud of inputs. And maybe in this diagram, I've alluded to how like the colors might be different, the size might be different, but the shapes are the same. Right? All right, so that's enough about the why. Let's talk about how we built export. Well, it was easy and it was hard. The easy part was that we were building all the shoulders of the PyTorch 2 compiler stack, and it has like a number of truly remarkable pieces of technology that inside that we could reuse. I can say this because I was not involved in building those things initially, so I can wholeheartedly kind of talk about how good it was. The hard part, in some sense, is that this is going against the grain of PyTorch. We are going against the spirit of eager, right? So we were always like anti-graphs and so on. So now we're talking about graphs, right? So we have to be very careful while we do this, right? Usability has always been a key feature of PyTorch, and usability has to be a top concern. How do we ensure that you even get to an exported graph, exported program, right? Um, and how do you how is that process kind of easy or hard for you? Can you understand the error messages and fix the code and things like that, right? There's also standardization that has to be a top concern, like how do runtimes ensure that they can run and then keep running your exported program over time? These are new things to think of. All right, so for the whole graph capture part, we are reusing Dynamo as is, right? So the story here is that you give example inputs, Dynamo traces through your code, gives you back a graph. We just want that graph to be like the entire graph for your computation, but other than that, technologically, we're just reusing that part. That's the easy part, right? The catch is that you might have to rewrite code. And today you have to rewrite this code manually. In the limit, probably you always have to manually rewrite code in order to get a whole graph. We can't promise that you will. We can do this automatically, although maybe in the future we might try to do a few things. Right. So partly this is because of how tracing compilers work. For example, control flow. Right. So we only ever take one possible path through your code. And we will often complain if it's not clear which path we are taking. If you want to capture more paths or all paths, you have to use some special control flow operators like torch.conf, right? So for the JAX folks, I mean this might be familiar, but for PyTorch folks, we have to introduce these operators, right? So you can imagine other control flow operators as well, like for loops and so on and maps, right? So you might have to do that. Now to guide you, we have built a database of examples, which we call ExportDB. This will grow over time, but the idea is that it will have a bunch of supported and non-supported examples. So you can learn what is expected to work and what is expected not work. And when you get errors, we often, in these errors, we link to the examples so that you can look at the examples and figure out, okay, what went wrong, what was I doing that was not so great, and how can I rewrite my code to fix it, right? So over time, we will polish this based on feedback, and we are committed to make it as easy as possible for you to export your code. All right, so let's talk about soundness. Dynamo is one of the key innovations of Dynamo is that I mean tracing is easy, but it is also sound. What that means is not only does it generate code for the path it traces, but it also returns these so-called guards that encode the conditions on the trace path, right? So so these guards, these conditions kind of guard the correctness of the code. So they are necessary conditions for the correctness of the code, right? So they were they are very easy to check by a machine, but they were never designed to be human readable, right? And that's fine because in eager mode, they don't need to be. Like these guards are checked internally. If they fail, we basically decide to recompile, right? So that's the whole reason why guards exist in the lab, right? To be checked, and if something goes wrong, we recompile, right? For export, we want to actually reuse these guards for something I'm going to just talk about, right? So for export, we are interested in conditions on the shapes of input tensors. And these are a subset of guards, which are called shape guards. All right, so we want to use these shape guards to establish a contract with the user. For that, we simplify these guards to sufficient conditions that are understandable by the user, right? So the original guards that were produced for necessary conditions, they're detailed, they have lots of arithmetic operations like, basically equations, symbolic equations, and then congruences and so on, lots of things. And if you're familiar with how symbolic shapes are implemented, it's quite nice. They use a solver called SymPy to do a lot of these kind of simplifications. We actually use SymPy in a sort of very kind of targeted ways to reduce these conditions to some things that are very easy for the user to understand. So once we have that contract, we would verify this contract at compile time. And obviously might get errors this way, but again, in the spirit of what we're trying to do, these errors will always be actionable in the sense that we will always tell you exactly what to do to fix these kind of specifications. And once you're there, we turn this contract into runtime assertions, so that at runtime, when you provide inputs that were not inside the contract, there's a clear error message at the very beginning rather than deep into it. The other part is that we assume static shapes by default, like all shapes are static by default. That's our basic assumption. So you don't have to do anything beyond that if that's all you wanted. So this contract would be completely implicit in that case, right? However, this basically means that the shapes of the future inputs has to exactly match the shapes of the example inputs, right? So this is just like static type inference. If that's not enough, sometimes you want to add generics to your program in other scenarios. So just like that, you can export your model with dynamic shapes, and then we would generalize, right? So classic example is that if you had an operator like maxmal in your code, right? Rather than specialize it to expect and return 4x4 tensors, because that's what you saw when you were feeding in example inputs. You can generalize that part of the code to expect tensor of shape A cross B and B cross C and give you back a tensor of shape A cross C. All right, so actually I want to kind of linger on this topic a bit more because it's kind of close to my heart. In a past life, I used to infer types for JavaScript. And when I looked at this, tensor shapes, there's actually a very strong analogy between types and shapes. In classic compilers like JavaScript compilers like V8 or whatever, you would rely on these types to be what they are, and then you would recompile based on guards if they were not. Tensor compilers do something that is very similar. So by default, if you had like a type for zip, let's say that takes two lists and gives you back a list, that's not a very nice type. And very similarly, matmul, you can say that it takes two tensors and returns a tensor. That's not very informative, right? But you can then do better and then specialize these types at particular element types. Like you zip a list of ints and a list of strings, and you get a list of tuples of ints and strings. Just like that, you could specialize the type of matmul to particular shapes. But the fully generic version of that is also possible, right? So this is the analogy, something maybe to think about is that in eager mode, we are dealing with dynamic types and we are okay recompiling your code. For export, the default is that we'll do static type inference or the equivalent of that based on your example inputs. And if you want more, then the user specifies how to generalize the shapes, and you can use symbolic shapes. All right. So hopefully that's enough whetting of appetite. Let's look at what export actually looks like. So this is the bare bones kind of toy example. You pass in a model or any callable really, and give it some example inputs, and we give you back an export program that you can call with other inputs as long as the shapes exactly match the shapes of the example inputs, right? So there's nothing much to see here, which is the whole point. This is often all you need to do to export your model. And in fact, we can automatically export a whole bunch of models in our open source benchmark suite, including a bunch of like Hugging Face and TEM models and so on, just by doing this. Like, of course, you may run into errors when you cannot get a full graph, in which case you will have to rewrite your code based on the examples that are linked to the error messages that we just talked about, right? So yeah, so this is that database of examples. Of course, like you'll get specific links for error messages, but you can go and browse this growing database where you have a bunch of examples that are kind of tricky, interesting examples that work or don't not work, and what the possible workarounds would be for those things. All right, so of course, like if you're not satisfied with just this, you want to generalize your inputs to different shapes, you can use dynamic shapes. And for that, we have an API that allows you to create a dimension. Let's say a common case is when you have a batch dimension that needs to vary over time, right? So you create a dimension called batch. This is internally is just like a symbol. And it kind of is one-to-one with the symbols that are used in the symbolic shapes implementation. And you can use this to create a dynamic shape specification for your inputs, and then you can pass it to your export call, right? And boom, you'll get an exported program that you can now call on inputs of different batch dimensions, right? So there's more to be said here. You can browse the API. For example, you may get errors again in this process, right? Maybe your code is not ready to be generalized. Maybe your batch dimension has to be exactly 32 because your code relies on the fact that it's exactly 32. In which case, generalization is not possible, and we should emit a good error message that tells you that is the case. Or maybe it's fine as long as it's between 16 and 512. And our API actually allows you to create dimensions with min and max values. So you can declare that and you'll be fine. If you don't, then we will give you exactly the line to fix in your code, right? So you just basically copy paste that suggestion and you should be fine, right? So we're kind of trying to make it easy for you to export your code. All right, so let's say finally you have an exported program. The whole point of this exercise was to do something with this so-called graph that we produced. And of course, you can write your own custom passes over this exported program, right? So underneath it is just a vanilla FX graph. If you're familiar with like FX format, it's just a graph of nodes. The nodes can be of 5 odd types, like call function, call method, get attribute, like that. So you can do whatever you want with this graph, right? So it's just that graph and then some additional information like source level metadata if you want a mapping back to your source, the original NN module structure that was flattened out. All of that information is there on the side. All the shape information is there on the side. But you do these transforms, you can replace ops, you can lower to your favorite IR. In fact, this is what many people were talking about here, lowering to HLO and other scenarios as well. So you can do all of that. Or you can kind of, if you want a front end, back end separation, you want all of this to be done kind of, in separate places, you can save and load an exported program, much like you would save and load an exported a normal model, except that here we're not just talking about model weights, but also model code and all of the extra information I just talked about, and also version information. So we also have versions. So you can imagine that there's a format for these exported programs, and we have a schema. It's kind of defined. Again, there are no stability guarantees yet, but we want to kind of have this kind of version control. Versioning. All right. So finally, something that people who are working on backends might be interested in. By default, an export program contains operators in the full A10 offset. These are all functionalized to simplify transformation. Backend authors can actually target a core subset of these operators for maximum coverage. And it is a simple API call to transform an export program to this subset. It's called run decompositions. It runs a set of like default decompositions that go from the full A10 offset to this core subset. You can also use this to plug in your own specialized operator implementations. So if you have special hardware to do convolutions, you can tell the API to avoid decomposing that particular operator, and then you can replace it with yours. I'm also not talking about support we have for custom ops. You can register the custom ops. I'm sure you guys are familiar with all of that in TensorFlow and things like that as well. So we have currently an API that allows you to register custom ops written in C++. And we're working on something that is ergonomic to use for Python as well. All right, so yeah, so that's all I wanted to talk about today regarding export. Yeah, please try it out. It's in the nightlies. So 2.1 had a version of export. We have been like changing it pretty frequently. So nightlies actually have some of the new APIs that I just talked about. Whereas if you go to the 2.1 docs, you will see another set of APIs. So sorry about that, but nightlies is your friend. There are no guarantees on stability yet, but we are working on a formal release soon. So hopefully, sometime in the near future, we can make more promises. Yeah, so there's a nightly tutorial as well. Again, if you go to the 2.1, there will be a tutorial on that page, but that will in turn link to this nightly tutorial, which has a bit more kind of information. Just so you know, this is not just a prototype. We have been using export internally with a lot of success. It's in fact powering AI inference on a bunch of Meta Reality Labs devices. We shipped with Ray-Ban Meta smart glasses soon, and that has some models that were exported. It's coming to Quest 3 VR headsets soon as well. There are some models there. It's also driving a bunch of next generation serving use cases. All this is made possible through integrations with ExecuTorch and IoT Inductor. These were two pieces of things that were talked about yesterday at the PyTorch conference as well. ExecuTorch got a bunch of press as well. And yeah, so we are also seeking broader community adoption through integrations with backends like TensorRT and Torch XLA. And we also have some ongoing partnerships for integrations with Apple, ARM, and Qualcomm. Yeah, so please use it and let us know what your experiences are using export. We are here to listen, support, and improve. Eager to get feedback. Thank you and happy hacking. Yeah.
Thank you, Vik. Any questions? Also, for virtual folks, we're taking questions on the OpenXLA Discord, which you can find in your email or on the GitHub page. Oh, there we go.
Thank you, great talk. My name is Milad from the PyTorch XLA team. I have two questions. Do you have any specifics on the limit on the number of dimensions that can be dynamic? That's the question number one. And the second question is, what's the level of support for data-dependent dynamism?
Yeah, so these are excellent questions that I wish. Do you know Edward Yang from the team? Yeah, so these would be perfect questions for him. I believe there is no logical limit to the dimensions, but there is in practice limit, which I couldn't tell you off the top of my head, on how large these dimensions can be. As for the other question, yes. So when you do a data dependent operation, we have no idea what the shape of the output will be. In which case, Dynamo used to basically choke because it really needs that information. Basically, it knows the shapes of your example inputs, so it can actually use that in the background, but it still needs to use the concrete shapes to decide which paths to take. So for data dependent operators, it could not. But recently, so we had two solutions. One that was ugly, which was we allowed the user to basically add a sort of assumption in line in your code that would tell Dynamo that, oh yeah, I mean, this is this is what I know about this shape, right? And then Dynamo could produce code that way. Recently, Ed is working on actually removing that. Because most of the time you use these results to actually create other tensors or do other things, and then you would know what assumptions are needed to create those things, right? So let's say you have an assumption that it has to be positive or it has to be between this and that, right? So there are certain classes of assertions that Dynamo would know that it's not a choice. You either have to pass those assertions or you have to fail tracing, in which case it would add those assumptions to the outputs of these data dependent operations. So most of the time, hopefully, you would not have to do much, and this would be supported. It's kind of getting there right now. The coverage of the ops that are supported are.
So today, you depend on the user to tell you.
There is a ugly API. We just removed that API and moved it and added an underscore to it because we are kind of hopeful that this can be done automatically in the near future. Like the user does not have to intervene.
Today, basically.
Yeah.
Hi, thank you very much for the talk. It was pretty informative. I have two quick questions. You mentioned customs. For customs, I guess you also provide a way to, I guess, give a shape function as well.
Yeah.
Okay.
It's called a meta kernel.
Oh yeah, got it. And the second question is, I wonder if you could elaborate a little bit on guards. So with dynamic shapes, we get guards. Are they also exportable, or there's basically a contract and a user needs to reproduce the same guards basically by some other means?
No, so guards are, let's think of guards as an implementation detail, right? So the guards, the actual sets of guards can change tomorrow if some SymPy chooses to change a little bit of the representation, and instead of doing ands of things, they just give you a list of things, whatever. So what we are trying to do is basically simplify those guards. And it's not very hard to do that. You throw like an inequality solver or some kind of congruence solver. It actually collapses all those conditions to something that's very easy to understand that, yeah, okay, you have to be between 2 and 5 or 2 and 10, and you have to be a multiple of 3 or something like that, right? So once we have that, that is the contract, right? So we bake in those things in the representation of the Explorer program. So today there are things like range constraints. You will see like if in the schema there's range constraints. So for symbols, that is what you have to satisfy.
So they captured in AR.
Yes, they are captured.
Got it. All right,
And then as I said, we turn them into runtime assertions as well. But they're there. Like if you're doing additional transforms, you can rely on the fact that that is the contract that we are expecting.
Got it. Thank you.
You can choose to ignore them, but then I'll be at your own.
It won't be sound.
Yeah.